Before we start thinking about differential equations, let's look at some examples of just how differential equations sort of come up in the wild, so to speak. So for example, let's think about a population that grows at a rate proportional to its own size. Let's try to describe this situation mathematically. So since there's a population whose size is changing, let's give the size of that population a name. How about P of t? So P for population and T for time. So P of t is the size of the population at time t. And the unit for this would be individuals, or individual people, or whatever it is that's in the population. So let's try to express this idea that the growth of this population is proportional to the size of the population. So the growth rate of the population, that would be a derivative. That's just the rate of change of the population with respect to time. So that would be d capital P d little t. So that's the left-hand side here, the growth rate of the population. And that is proportional to the size of the population. So is means equals. And proportional to means that it's a constant multiple of. So some multiple, so k is a constant here. That will probably depend on what kind of population it is, I guess. Proportional to the size of the population. Well, the size of the population is P, or P of t. So here's an equation, but it's a funny sort of equation. The unknown thing in this equation is the function P of t. In algebraic equations, we're used to the unknown being a variable, and what we're looking for is just a number. But in this situation, the unknown thing is a function of some independent variable, and the equation has the function in it, but also a derivative of the function. And that's why this is called a differential equation. It's because a derivative shows up. Let's look at another example. So let's think about Newton's second law, which says force is mass times acceleration. Well, it takes a little context here, so let's add some information to the situation. Let's suppose that we have some object that just moves back and forth in a straight line, so we can measure its position with, say, a ruler. And let's call its position at time t x. So x is the position at time t. In many situations, the force experienced by an object only depends on where it is. And so in that situation, the force would be just a function of x. So this is force at position x. Okay, so we have an interpretation for the force F. The mass, well, let's say this is just an object of mass m. So force equals mass times acceleration. What is acceleration in this situation? Well, acceleration is the second time derivative of x, the position. Right? The first time derivative of x is the velocity of the object, and so the second time derivative is the acceleration. And so when we translate Newton's second law into this notation, what we get is f of x equals mass, which is a constant usually in some situations, mass times the second derivative of x. And so again, in this situation, we have an unknown function x of t and its derivatives. In this case, just its second derivative. And again, that's what makes this a differential equation. There's an unknown function, and the equation relates the unknown function and its derivatives. Okay, third example. Let's suppose we have a function that tells you the position of a string at time t when you're watching a position x units from one end. So you see here I've gotten this function u written as a function of two variables, and that's because to tell the position of a string as it wobbles back and forth, maybe like this, you need to know not just at what position you're watching, but also at what time you're watching, because as time goes on, this part of the string is going to move up and down, and this part over here is going to move up and down. Every part of the string is going to move up and down. So to know where the string is, you have to know not just where you're watching it, but also what time it is. And that's why this function u, that is the position of the string, has to be a function of two variables, position and time. If you do some physics or ask a physicist to tell you what the appropriate equation to describe the motion of a string like this is, what they'll tell you is the second derivative of u with respect to t is equal to some constant, so again k here is a constant, times the second derivative of u with respect to x. Now these funny looking d's, these are partial derivatives. And if you don't know what partial derivatives are, don't worry about it, because the types of differential equations where partial derivatives show up, we're not going to study in this class. But again, in this situation, we have an unknown function, u of x comma t, and its derivatives. And so that's what makes a differential equation a differential equation. There's some unknown function, and the equation relates the unknown function and its derivatives. All right, but that's a pretty general idea. There are lots of different types of differential equations, and what we'll see is that there are lots of tricks for working with differential equations, but no trick works for every kind of equation. And so we'll have to classify differential equations to know what kind of tricks or techniques to use. And one of the major categories of differential equations is partial differential equations versus ordinary differential equations. So if you think back to that example with the string, where we had second derivative with respect to time is a constant times second derivative with respect to position. Since these derivatives are partial derivatives, that makes this a partial differential equation, or PDE for short. So in a PDE, the unknown function is a function of more than one independent variable. And in this class, this is not the kind of differential equation we're studying. It is an important kind of differential equation. Lots of physical situations produce partial differential equations, but partial differential equations sort of are kind of next level compared to the sorts of differential equations we're going to be looking at. You have to learn to walk before you can run. And so the type of differential equation we'll be studying are called ordinary differential equations. In ordinary differential equations, the unknown function is a function of a single independent variable. So this is more like the population example where we had dp dt equals some function of p, and our unknown was a function only of a single variable. So in this class, we're only going to be looking at ordinary differential equations. All right. But even among ordinary differential equations, there are a few different types that are good to know about. One major feature of a differential equation is the order of the differential equation. And the order of a differential equation is just the highest derivative that appears in the equation. So for example, in this population equation, dp dt equals k times t, the highest order derivative is just the first derivative, dp dt. So first derivative. And so we say that this differential equation has order 1, or is first order. And that in the example with Newton's second law, where we said f of x equals mass times x double prime, well, here this highest order derivative is the second derivative. So this would be second order. In principle, you could have a differential equation of any order that's a positive integer. We'll see that, at least for the situations we're going to look at, first order and second order equations show up, but higher order than that tend not to. It really depends on the field you're working in, though. So, you know, depending on what you study, you might run into higher order equations. Another major division among types of differential equations, and here we're still talking ordinary differential equations, is whether they're linear or not. So as with regular algebraic equations, linear equations are the nicest. We'll see why later. And equations that aren't linear tend to be messier in general. So a linear ordinary differential equation is one that looks like this. So in this setup, our our unknown function is called y, and x is our independent variable in this situation. And what makes this linear is you have derivatives of y, and here, so here's the nth derivative, the n minus first derivative, and so on, down to the first derivative, and then, well, I'm missing a term here. I need a term with the 0th derivative of y, which is just y with no derivatives at all, plus possibly a term that doesn't have y in it at all. There we go, that's the right form. So what makes this linear is you have derivatives of y of any order, even down to no derivatives and even without y at all, and they're all multiplied by functions of the independent variable. Okay, so this is what makes a linear differential equation. And of course, this particular linear differential equation that I've written down happens to be of order n, because n is the highest order derivative that shows up right there. Of course, any differential equation that isn't linear is called nonlinear, so that's very creative. Let's look at a few examples. So our population example, dp dt equals k times p. It doesn't look exactly like this form, but we could rearrange this. If you move the p term to the left, you get dp dt minus k times p equals 0. And that matches this form because, right, we have an order 1 term times some function of t, which is just the constant function 1, plus the 0th order derivative of p, which is just p itself, times another constant function. Okay, so a lot of these terms in our template up here are 0 in this particular example. So our population equation does fit this template of being linear, so it is linear. If you look at our Newton's second law equation, again, we need to rearrange it a little bit, but when you rearrange it, it looks like f of x minus m times x double prime equals 0. And again, this is linear because there's derivatives. Actually, I guess whether this is linear or not depends on what exactly this function is doing to x. So I guess for this one, we can't say if this is linear or not. But let's look at a few other examples to see what sort of things count as linear. So for example, how about this equation? Y double prime minus 3y prime plus 4y equals 0. Is that linear? Yeah, this is linear. We have a second derivative term times a function of the independent variable. and again, it's times 1. We have a first derivative times a function of the independent variable, which is a constant function in this case, and the zero derivative term times a function of the independent variable. So yes, this is linear. Okay, what about something like y prime, x times y prime plus 1 over x times y plus x equals 0? Is this linear? Well, it has a y prime term times a function of x, it has a y term times a function of x, and it has a term that doesn't have any y's in it, and they're all added together. So yes, this is linear. As you can see, there are lots of things that are linear equations. That's one thing that makes working with linear equations so nice. A lot of common equations are linear. Let's look at another example. How about y squared plus y prime equals 0? Is that linear? Well, does it match this template up here? The only place that y shows up in our linear template is in derivatives, and then by itself with no exponent in this term here. But in the equation y squared plus y prime equals 0, y is showing up squared, but that never happens in our template, so this isn't linear. This is nonlinear. Probably it shouldn't be a surprise that when you have y squared, it's not linear. Let's look at one other example. How about y prime times y minus x equals 0? Is that linear? Well, if you look at our template for what counts as a linear equation, none of these derivatives of y are multiplied with other derivatives of y. They can all be multiplied by functions of x, but they can't be multiplied by other derivatives of y. So in the equation y prime times y minus x equals 0, this term right here, it has a product of two derivatives of y, and that's not allowed in a linear equation. So this equation is also nonlinear. The reason why it's so important to make a distinction between linear and nonlinear equations is because a lot of the tricks that we will figure out for linear equations won't at all work for nonlinear equations.